So good morning, everyone, and sorry I couldn't make it. Originally, I was supposed to be moving to Australia, and that didn't quite work out, and this was supposed to be a side trip. So I thought this morning I would try and give a little bit of perspective about sort of how we face durability issues. And the first slide should be a picture of a field test site, I hope. Yes?
Yes, it is.
Good. Okay, so that is our field site, which dates back to 1927. And we've been involved in durability for obviously over almost 100 years because it's a really important aspect of how we use timber. But it's sort of a little bit different than the rest of the world does. And so next slide, please. I'd like to kind of call this durability American style. And I apologize because that's not the American style of our current president. It's a better American style. But if you could go to the next slide, please, Clemens. So we have a sort of a very strange system because we don't really deal with durability the way most of the world does. You have categories and durability classes, and we don't have those here. So our durability classification is mostly related to treated wood. And we have the same category system you have. You have a hazard class, we have a use category, but they're very much the same. But their natural durability is not considered. And it's sort of a strange system when you think about how much durable wood we have, but it's sort of how we've evolved. And it mostly relates to where the durable wood is used and where the treated wood is used. So if you can go to the next slide, please. So our durability classification for natural durability is based on laboratory tests. And what you'll see in front of you is the standard from ASTM, Standard D 2017, which is not even a valid standard anymore, but we still use it. It's out of date. And we classify based on the mass loss of small little tiny blocks in decay tests. And there's no standard process for doing that other than listing, and you can see we go from highly resistant to slightly to non-resistant in our woods. It's not a very good system, but it's sort of how we've evolved. And we've done that. We've made attempts at trying to classify durability, but it really hasn't worked well because we cannot come to consensus on how it should be done. And we don't have the regulatory systems that you have. All of our standards are voluntary. And even though they're in our building codes, there's no real teeth into how we would make a system work. And so there's not a lot of incentive on the part of users. So if you could go to the next slide, please. Our naturally durable woods are mostly used for things. The biggest market in the US would be decking, or in North America would be decking. And after that, we would look for outdoor living, and that could be things like gazebos and play structures and other naturally places where people are very afraid of using pesticides, even though naturally durable woods are very good pesticides. And so they tend to go towards cedar and other products. We still use cedar utility poles, so naturally durable utility poles are an important part of our electric distribution system. It represents about 5 to 10% of the market there. And then you see lots of things for fence posts and other applications, but by and large, we don't use naturally durable woods for a lot of structural applications, which is why you don't see there's a standard. Next slide, please. All right. So we have a species of, unlike the projects you're looking at now, where you're looking at eucalyptus, most of our commercially important naturally durable woods are softwoods. And you can see that we use western red cedar, we use coastal redwood, and we use Alaska cedar as some of the bigger species. And obviously, you've got western red cedar, coast redwood growing in New Zealand also. You've stolen them from us, and hopefully they will there. But we also have some incredibly durable hardwoods, and we don't use them very much commercially. But Osage orange would be my best example. That field site I showed you in the beginning, the first slide, we have posts out there that date to 1935 of Osage orange. And they are as sound as the day they were put in the ground. So we do have some incredibly useful hardwoods. Black locust would be the other species. And if you want to click to the next slide, Clemens, that'd be great. So hopefully, let me flip over and figure out where I am. This should be a picture of kind of how we use. So we've always used natural durability. We have some totem poles here, and Native Americans used western red cedar and Alaska cedar as part of their cultural heritage because they knew they were durable. Next slide, please. We use western red cedar for decking and gazebos and lots of other products. And then next slide. And then the same thing for coast redwood, which is a fairly important, valuable species that grows in Oregon and Washington, Oregon and California on the coastal areas. We also drive through our trees, and I don't think that's something you can do in New Zealand. But these species are fairly important, and they are changing. We know that redwood is already losing some of its inherent durability in second growth material, and there have been a number of papers about that. Western red cedar really hasn't come to that point yet, but we know it might get there because most of the trees we're still harvesting are 80 to 150 years old, and so we're still harvesting fairly older material. But when we get to the plantation resources that are being put in, that may become a problem for us. And so we are concerned about durability will go. And then we do have, as I mentioned, two other species. Next slide, please. Black locust, which is a durable, very durable heartwood. In fact, it was carried by our pioneers across the western United States to plant for hedgerows in their farms, and it's a very good fence post material. And then the next one up was what I mentioned is Osage orange, which has got to be the most spectacular, cool tree because it produces this big fruit that's the size of basically a grapefruit. And as I mentioned, it's very durable. And then the other thing we do is we do import some timbers, some of which you also do. Next slide, please. And so we import things like Morrell. In our side of the continent, we have species like Ipe, Purple Heart, Angelique that are very, very durable tropical hardwoods, but they carry with them the environmental implications of this may not be a good thing to do because you're stripping native forest in the tropics. And so there are some issues related to that. Most of that market is very high-end decking, or it's a lot of these species actually get used inside the beds of refrigerated trucks, which seems like an odd place for wood to wind up, but it winds up between the aluminum layers and works out as a good cushion material. So, but imported timbers aren't that important to us. It's mostly our native timbers that we use. Next slide, please. So our durability issues are probably the same ones you guys are looking at. One is supply. We just don't have enough that would meet the need. Two is the variability between species, and that's one I'll come back to later because we see that as a big factor. We can take two trees in the same stand and get very different durability rates. I know that I can take 25 posts and put them in the ground. I pretty much know from my data that 5 of them will fail within 10 years. 5 of them will last way longer than they should, and the rest will fail where they should be. And it depends on the species, but there's a lot of variability within that, which makes it hard to use as an engineered material. We have issues about second growth because of the amount of sapwood. And the slide you're looking at shows teak, which I think is the best. It's like the poster child of natural durability and to do it. There are teak plantations all over the world. They grow really fast. Everybody loves them, but there's a lot of sapwood in them. And so we worry about the same issues with cedar and redwood. We see a lot of sapwood in our second growth cedar. And so it'll be an important problem for us. Next, please. So why don't we standardize? You have great standards. You have durability classes. Europe has durability classes. We go our own way and say we don't need durability classes, or in the United States, we'd say we don't need no stinking durability classes. The difficulty we have is right now there's not a good system for verifying what people are buying. That's one problem. There's total lack of supplier interest in doing it. Nobody seems to be concerned. They like the idea that they can just go do a few soil block tests and come up with a durability classification for the materials. And we see some really dramatic differences. The best example would be Cryptomeria, the Japanese species. There are some places where it's very durable in plantation and some other places where it's not, and it's totally based on seed source, because even growing in the same area, you see that range of durability. That's something that people are going to have to face around the world. We haven't gotten there yet. And then there's no real consumer interest. The consumers in the United States are not what you particularly call astute. And I've seen people buying whole cartloads of Western red cedar that are almost all sapwood. And when you explain to them that that's not really a very good thing to do, they say, well, I'm going to coat it with a preservative. And when you explain that won't work, they sort of just look at you and shake their heads and walk away. So we don't have the consumer who would demand that kind of a product. We do see naturally durable woods used in one code application, and that's for the sill plates of buildings. But it's the only place we see it. So in our codes, it really doesn't show up. But globally, I think there's the need for a non-destructive method for assessing durability. And that's what I have one of my PhD students right now. And so I want to talk about that. And so next slide, please. We're trying to look at relatively rapid non-destructive durability assessment. And our premise is that you don't really need to be really precise about this, because what you're trying to do is sort good from bad. And if all you need to do is good from bad, you can throw out a lot of bad. And you can have a fairly high bar or a low bar, depending on what you're looking at. And so it allows you to sort of parse things out in a relatively simple. Next slide. So what we're looking at right now are our species, because we have them and you don't. Western red cedar is Western juniper, which is a dry land species. Actually would fit in quite well in New Zealand, but it'd probably escape and you'd have to eradicate it later. Alaska, well, it's like your lodgepole pine. It would do the same thing. Alaska cedar and Western red cedar are the species we're looking at. And what we've done is we've gotten a lot of stems of freshly cut material, and we're cutting radial transects. And then we're taking those and looking at decay resistance, extractives content, termite resistance, because we do have termites here. And we're trying to correlate that with non-destructive tools. So we're trying to come back to some measure of what's there. The ultimate goal of this, because the student is from Malaysia, is that this would be used on tropical hardwoods. So that's our end game. But for now, we're using species that we can get hold of. And the two tools we're looking at right now are near infrared and Fourier transform infrared spectroscopy, because they're relatively simple. Well, they're not simple, but they're relatively they're non-destructive, they're fast, they require interpretation, but they're tools that we feel could be automated relatively quickly. And so next slide, please. We are just getting into near infrared. My colleague Laurie Shimlick, who's actually an Australian, is now helping us with that. But near infrared has some usefulness because it contains a lot of information within the spectra. And the problem you have with near infrared is that it contains a lot of information in the spectra, and it's really hard to sort. And so you do a lot of massaging with the data using things like principal components analysis that lets you pick out elements of the curve that you want to look at. We are just beginning to look at that, but there are some previous reports of trying to do that. We've tried it, and it hasn't worked very well for the species we looked at, but we didn't look at it to the degree we're looking at it now. We think that might have some application, but we are just beginning to look at that. Next slide, please. The other alternative is Fourier transforms infrared spectroscopy, which uses a fairly broad range of the spectra. But the idea is you can get surface chemistry data from it. You can get fairly specific molecular data inferred from the spectra, which allows you to begin to figure out what might be present and how much of it might be there. Again, it's non-destructive. It's much more involved than the near infrared in terms of understanding the spectra. But the information contained is actually pretty useful. And the technologies, the computer technologies are expanding and advancing so quickly that we feel that it's not that far away from it being some type of a field portable instrument that could be used. So it has the potential for going out and being put into some type of a mill operation as a sorting tool. That's kind of next slide. So what we've done, hopefully, is we're looking at extractive-free Alaska cedar to start. And Alaska cedar, for those not familiar with it, obviously grows in Alaska, but it grows up and down our west coast. It is where in Oregon it's actually a remnant of the last glacial period, the last ice age. It has a very, very durable heartwood. In fact, much better than I think Western red cedar. It has it's invisible heartwood. It doesn't have a visible color to the heartwood, so it's difficult to sort. So it's a species that's sort of interesting for us. And what we've gotten is a number of Alaska cedar samples from different sources. And then we extracted all of the native extractives from it. And then we wanted to reintroduce extractives at levels we could measure, because we're trying to quantify and develop some standard curves. And so we looked at carvacrol, which is one of the more important extractives in the species. And we basically put back in 1 to 10% carvacrol. And we recognize this is not the best way to go, but it allows us to try and sort out what extractives are important and whether we can quantify them or not. And then we did FTIR analysis of the solid wood, and then we ground materials and looked with potassium bromide pellets, so KBR pellets. And then we looked at the spectra to examine for shapes we might want to find changes. So next slide, please. This is a spectra of a sample extracted and non-extracted, and you begin to see there's a whole lot of peaks there. And some of them may be important, some of them may not be. But you can see that there's a slight change when you extract all the extractives out of the wood. You do get loss of some peaks, which would be the extractives we're looking for. And then the next slide, please. This next slide is sort of taking that broader spectrum, which went all the way for the full scan of the FTIR, and then going down to a narrower range. You'll have to forgive the American accent here, or as they would say, New York accent, which is even worse. So you can take these kind of spectra and then overlay them. And so the next slide is really what we're looking at, overlaying all the spectra of all the samples we've looked at. And you can begin to see peaks emerge and disappear as you change the concentrations. So this is where we think you can go to look at the possibilities for looking at extractives content. This is non-destructive, so it allows you to go back and do some repeated measures and do some other things with the material that you couldn't necessarily do if you had to destroy the material. When you start to plot these data, what we've done is we've taken peaks, known peaks from the polymers themselves, so cellulose, hemicellulose, and lignin. We've taken those wavelengths and then set up ratios for what we think are the extractives versus what are the standard materials that would always be present in the wood. So we have a baseline in every piece of wood, so we can sort of auto-correct for different material levels. And the next two slides are exactly that, where we've taken the extractives, the ratios between specific peaks that correspond to things like hemicellulose and cellulose, and then corresponding those to what would be a carvacrol peak or an extractives peak. And you begin to see trends, not as good as we'd like, because this is sort of our first shot through, but you do see a relationship between concentration of carvacrol and the peak ratios. And so the next one shows that also, in this case, getting a little more specific with ratio. So we see possibilities here. And the next steps are really taking this and exploring it on other species. As I said, we have western red cedar or western juniper, which have obviously different extractive components. We haven't even brought this to a hardwood yet, but the idea is that you could begin to see kind of gross changes in extractives content, which would then be related back to the durability. You would obviously have to do this for every species. So there's a big startup here. I would say that that's not that different than some of the other activities I've seen recently. I know in Australia, when they're trying to certify things like Morrell, they're going out and looking at DNA in stands. And so this is akin to that, is going out and actually quantifying sort of the durability of a stand. This might allow you in breeding programs to go out and non-destructively assess once you started to see heart formation, which obviously is further down the line, but it's a starting point for being able to do that. Next slide, please. So I think what we see now is we have a reasonable ability to predict carvacrol being present. We have a relationship which sort of gets mucked up in a few places, but it basically tells us kind of what we're looking at. The ATR approach we've looked at hasn't been very good yet because it's just too variable. It just doesn't give us the information we want because we don't fully understand the spectra. Once we get the spectra down and understand it, I think surface chemistry measures will be pretty quick, and that will give us a way to do that. But we really need to work on sort of the next steps, and that's kind of looking at a lot more samples, a lot more breakdown of what we're doing. But the ultimate objective of looking at this slide. Next slide. Should be next slide. The ultimate objective really is we want something that we think will assess durability on the fly, that a board would come down the chute and it would be assessed non-destructively, and you would instantly know whether something. And you probably, knowing lumber dealers, they'd sell the other stuff anyway, because that's just the way it goes. But you would have some possibility of having some new was exceptionally good, and this would allow people to maybe get a premium for it. It would also allow people to sort a little bit more on species when you get into mixes, particularly when you get into a lot of tropical hardwoods where you wind up with Nitsia species, which have a lot of different variables in there. We think that has a possibility as well. So hopefully by the end of October, because the student has to finish, we will have a much better answer where we're going. But this is sort of a starting point. And then with the last slide, I would thank you for your time because I'm going to go pretty quick. So is the last slide? That's the last slide. That's the story bridge. where I'd very much like to be right now. I entertain any questions.